All right, this is the solutions to the Unit 1 exam for Physics 1402. All right, let's go through this quickly. So we have paths of, various paths that a particle can take in an electric field. We know a charge of negative 3q follows path 2, so it's negative 3q. In which direction does the electric field point? Well, the electric field has to point downward like this. And the reason being is that a positively charged particle will experience a force in the direction of the electric field. A negatively charged particle will feel a force in the opposite direction. So since the negatively charged particle is curved upwards, the electric field must point downward. Which path would be followed by a helium atom electrically neutral particle, charge 3? Well, I'll describe this because force is opposite to E field when Q is negative. Which path would be followed by helium electrically neutral? That would be 3. No charge. No electric force. Which path would be followed by a charge plus 6q? Why? Well, it's going to have to be 5 because, for one thing, it's going to be in the opposite direction because it's an opposite charge. Whoops. The opposite charge, opposite direction. I guess I should have drawn the arrow like that. We also know that the magnitude of the force must be greater, I'll say the magnitude of the force for, what do we call it, plus 6q must be greater than the magnitude of the force for minus 3q. So it must curve more. Simple enough? Okay, so in the next problem, you have 4-point charges at the corner of a square, and you want to know what the electric field is at point P in the center. Well, I mentioned that you should always think about symmetry here because this point charge is going to create a field in that direction, and that point charge is going to create a field in the same direct, or in the opposite direction, excuse me. So these 2 point charges are going to create fields that cancel out, and I'm not even going to bother with calculating them. Now you have this charge creating a field in this direction, and this negative charge creating a field in the same direction. So they're going to add together, and they're along the same line, so I don't have to break it down into vectors or anything. All I'm going to do is, let me angle this camera a little bit. All I'm going to do is take the equation E equals K, Q1, I'll call this 1, and this 2, over R squared, plus K, Q2 over R squared. I'm not going to worry about signs or anything, but I know both of these fields are going to be in the same direction, so they will add together. So I'm just going to take the absolute value of these 2 charges. I also know the distance from P to the charge is the same in each one, so I can pull out K over R squared times Q1 plus Q2. What is this distance? Well, if I call this A, like A equals 2 meters and B equals 2 meters, I can draw a triangle where this is point P and this is the other point charge, so this is A over 2, R, and this is B over 2. See, B over 2, A over 2. All right, so then R equals the square root of A over 2 squared plus B over 2 squared, but A and B are the same thing, so A equals square root of 2 times A over 2 squared, which then means A equals square root of a squared over 2, which equals 1 over square root of 2 times a. All right, or a over square root of 2. So then the electric field, I can come plug that in. A over square root of 2 squared times Q1 plus Q2, which is equal to, this squared is going to be 2, so that's going to be 2K over A squared times Q1 plus Q2, and I'll keep those absolute value things around. So now I can just start plugging stuff in. 2 times 8.99, which is K, times 10 to the 9th Newton meter squared per Coulomb squared, times Q1, 3 times 10 to the negative 6 coulombs, plus 1 times 10 to the negative 6 coulombs. And that's all going to be over A squared, which is just 2 meters squared. So I'll punch that in my calculator. So it's 8.99 10 to the 9th times 2 times 3 10 to the negative 6th plus 1 10 to the negative 6th divided by 4. E equals 1.79, well, I guess that's about 1.80 times 10 to the 4th newtons per coulomb. All right. Now we have an equipotential plot. How much work is required to move the -1 microcoulomb charge from B to D to C? B to D to C. Well, work is equal to the negative change in potential energy, which equals the negative change in potential energy is going to be Q delta V, right? Which, what is delta V? B to D to C, that's 0. Change in voltage is 0. Therefore, work equals 0. Now, a positive point charge is placed at F. When it is released, describe what happens. A diagram may be helpful. Well, if it's a positive point charge, it's going to feel a force that pushes it towards the more negative, lower potential, I'll put it that way. So, but the force is also going to be perpendicular to the equipotential line, so the force is going to be like that. So, is toward lower potential at perpendicular orientation to equipotential line. What is the magnitude of the electric field at point A? Well, the electric field is negative change in voltage over change in distance, displacement. So that equals negative change in voltage. Let's say from here to here, delta V equals, well, I'll write it out, V final minus V initial over X final minus X initial. So V final would be plus 40 minus initial, which is plus, actually let's take it all the way out here, 0. So I can put that 0 in there. So it's from here to here. It doesn't matter what I choose. The field's going to be the same because all these lines are parallel. And X final is 0.4 meters and X initial is 0. All right, so the electric field then is going to be 40 volts over 0.4 meters, which will be, what, 100? And that's volts per meter. Excuse me, I lost a negative over there. Negative, negative, negative. So E equals negative 100 volts per meter, which means it's going to be in this direction, which makes sense because it points from higher voltage to lower voltage. So the electric field is negative here. Two protons are moving directly towards one another. When they are very far apart, their initial speeds are 0.0 times 10 to the 6 meters per second. What is the distance of closest approach? Well, here we would use the energy balance. E0 equals E final. In the beginning, they are very far apart. That means electric potential energy, we'll just set that equal to 0. So in the beginning, we just have kinetic energy. And in the end, they're going to come to a stopping point. So KE final equals 0. Well, I'll do it like this. EPE0 equals KE final plus EPE final. We said electric potential energy in the beginning is 0, and in the end, kinetic energy equals 0. So I could say kinetic energy in the beginning equals electric potential energy in the end, which is like saying KE10 plus KE20, because they're both moving towards one another, equals EPE final. Or 2 KE1 initial, because they're going to have the same kinetic energy because they're moving with the same speed, and EPE is going to be Q delta V. Or I should say KQ over R, because it's going to be, the potential is going to be charge 1 with coming into the potential set up by charge 2, right? So if I want to say it like that, either way, I mean, you do 2, 1, 1, 2, whatever. So now I'll solve for R. Equals K Q1 Q2 over 2KE equals K Q1 Q2 over 2 times 1/2 mv squared. And I just realized I've got to look up the mass of a proton. Which this is like saying, though, KE squared over mv squared. Okay, so plugging in our numbers, R equals K, which is 8.99 times 10 to the negative 10 to the 9th, positive 9th. Newton meter squared per coulomb squared, times the charge of a proton, 1.60 times 10 to the negative 19th coulombs squared, over the mass of a proton, 1.67 times 10 to the negative 27th kilograms, times the velocity given to us in the problem, 3.00 times 10 to the 6th meters per second, and that is squared. Punch that into my calculator. 8.99, 10 to the 9th, I guess I can do it here so you can see it, to the 9th times 1.6, negative 19th, I'm going to square that, divided by, I'll put parentheses here, 1.67, negative 27 times 3 times 10 to the 6th squared, close parentheses, R equals 1.53 times 10 to the negative 14th meters. All right. K is 8.99 times 10 to the 9th. What are the newtons meter squared per coulomb squared? E is 1.60 times 10 to the negative 9th coulombs. Mass is Gotta look that up. I have to add that to your test. .67 times 10 to the negative 27th kilograms, and velocity is given to us in the problem 3.00 times 10 to the 6th meters per second. And I'm just punching it in the calculator now. Oh, negative 19th. That's the problem. Squared. .59 times 10 to the negative 8th meters. Squared up there. All right. 3 resistors are placed in the circuit as shown. The potential difference between points A and B is 30 volts. What is the equivalent resistance between points A and B? Well, first thing we need to do is combine these 2 resistors, where this is R1 and this is R23. R23 is going to equal the inverse of R2 plus the inverse of R3 and the inverse of all of that. So R23 is equal to 60 ohms inverse plus 30 ohms inverse. Let's see, 60 inverse plus 30 inverse. So it's going to be 20. I've called this 1, 2, 3. R123. R123 equals R1 plus R23. R123 equals then R1, which is 10 ohms, plus R23, which is, oh, that should be 20, excuse me. Equals 30 ohms. Okay, so R123 equals 30 ohms. So now the next problem says, what is the potential drop across the 10 ohm resistor? Well, first I need to find the current through the whole thing. So if I go to 3, so the current in 1, 2, 3 is equal to the voltage across 1, 2, 3 over the resistance of 1, 2, 3, which equals 30 volts over 30 ohms, so it equals 1 amp through the whole thing. And if we go back to 2, this is R1 and this is R123. I1 equals I123, which equals 1 amp. The current through this is the same as current through that. Oh, I'm sorry, it's asking for the voltage. Whoopsie. Well, we do need to know that. So I1 equals I123 equals 1 amp. And the voltage across 1 is going to be I1 times R1, which equals 1 amp times 10 ohms. V1 equals 10 volts. Oh, I'm sorry, I'm off the page. Simple enough, right? What is the potential drop across the 30 ohm resistor? Okay, well, we know now that coming in here, well, let me draw it again. If we look at circuit 2, R1, R2, 3. Oh, that up there was wrong. It should have been 2, 3. So we know the current coming in here. That's just equal to I1 or I1, 2, 3. So we can find the voltage drop across R23. R V23 is equal to I23 times R23, which is equal to I123 times R23. Our I123 is 1 amp. R23 is equal to, well, we found it back here, it's equal to 20 ohms. So the voltage drop is 20 volts across this. That means going back to 1, oops, R1, R2, R3, we know that from here to here is 20 volts. So we also know from here to here is 20 volts and from here to here is 20 volts. So V3 equals V23 equals 20 volts. And we just solved the problem. And that's the test.